Hi class. In this lecture we continue our study of functions by moving into what we call one-to-one functions and their inverses. So we'll be learning about what it means for a function to be one-to-one, and what we're going to define is something called an inverse function. Alright, so our objectives talk about one-to-one functions, the inverse of a function, talk about finding the inverse of a function, and then graphing the inverse of a function. Alright, so first, the inverse of a function is a rule that acts on the output of a function and produces the corresponding input. So it basically, what an inverse does is it undoes or reverses the function, what the function has done. All right, so it's important to note that not all functions have inverses. Those that do are what we call one-to-one functions. Okay, so what is a one-to-one function? So let's compare the functions f and g, whose arrow diagrams are shown here. This here, if you notice, this function f of f is what we call one-to-one because each input goes to exactly one output, okay? This function g here is not one-to-one, all right, because the inputs 3 and 2 go to the same output, okay? So each input does not go to a distinct output, okay? Here, these two inputs went to the same output, not one-to-one. Okay, so definition here, a function with domain A is called one-to-one if no two elements of A have the same image. Okay, that is, you can never have f of x1 be equal to f of x2. They always must be different whenever the x values are different. So an equivalent way of writing the condition of one-to-one is that if you have f of x1 is equal to f of x2, the only way that can happen is when x1 is the same as x2. Otherwise, they're not one-to-one. So if a horizontal line intersects the graph of f at more than one point, then we see from figure 2 that there are the numbers x1 is not equal to x2, but we see that f of x1 is equal to f of x2. Okay, this means that f is not one-to-one. Okay, so if you notice here, what this is saying is x1 produces this value, x2 produces the same value, not one-to-one. So therefore, we have the following geometric method for determining whether a function is one-to-one. Okay, a function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay. So just as we use the vertical line test to determine if a graph was a function, we can use the horizontal line test to determine if a graph or if a function is one-to-one. All right, so let's look at this one. Is the function f of x equal to x cubed one-to-one? Well, if x1 is not equal to x2, then it must be the case that x1 cubed is not equal to x2 cubed. So two different numbers cannot have the same cube. All right, therefore we know that's true, so x to the third power is one-to-one. Also, you can do this horizontal line test. If you sketch the graph of f of x is equal to x cubed, and you draw horizontal lines through it, they only intersect it once. So this has to be one-to-one. Note, though, that if you actually drew f of x is equal to x squared and drew a horizontal line through it, it would not be one-to-one because the graph, your horizontal lines would intersect the graph more than once. All right, let's talk about now the inverse of a function. One-to-one functions are important because they are precisely the functions that process inverse functions according to the following definition. Okay, so let's let f be a one-to-one function with domain A in range B. Okay, then its inverse function we denote as f with the -1 sign. Okay, that doesn't mean f raised to the -1 power. That's important to note. Okay, f of -1 has domain B, so the range here was B, but now over here it's the domain in range A, right, and is defined by the following. All right, f inverse of y is equal to A is an equivalent statement of f of x is equal to y. So it reverses the domain and range. Okay, it reverses it. All right, this definition says that if f takes x to y, then f inverse, that f -1, f inverse takes y back to x. If f were not one-to-one, then f inverse would not be defined uniquely. Important. All right, the arrow diagram we see below indicates that f inverse reverses the effect of f. So from this definition, we have the following. First off, notice that for the function f, we take x to y. For the inverse function, we take y, and it gives us x. So the domain of f inverse is the range of f, and the range of f inverse is the domain of f. So if you know the original function's domain and range, you also know the domain and range of the inverse function. It's just the opposite, or the reverse of them. All right, let's do an example. So for specific values. If we have our function f of 1 is equal to 5, and f of 3 is equal to 7, and f of 8 is equal to negative 10, let's find f inverse of 5, f inverse of 7, and f inverse of negative 10. All right, from the definition, we have the following. F inverse of 5, remember, it undoes it, okay? So in the original function, 1 went to 5. So in the inverse function, 5 must go to 1. Okay, so f inverse of 5 is 1. Same thing here. In the original function, 3 went to 7, so in the inverse, 7 has to go to 3. F inverse of negative 10, well, in the original function, 8 went to negative 10, so in the inverse, negative 10 has to go to 8. All right, so this figure 7 here shows how f inverse reverses the effect of the original function f in this case. Okay, that's all you're seeing. We're just switching the arrow. We're switching the correspondence, okay? In the original function, 1 goes to 5. In the inverse function, 5 goes to 1. That's what we're saying here. Important, as I was saying here, don't mistake this negative 1 and negative 1 for an exponent. That's not what this is saying, okay? All right. The reciprocal of the original function f of x is written as in parentheses with the negative 1 outside. So when this negative 1 is tucked right here, always going to imply the inverse. Incredibly important. All right, so by definition, the inverse function f to negative 1, f inverse, undoes what f does, okay? If we start with x, apply f, and then apply f inverse, we arrive back at x, all right, where we started. Similarly, f undoes what f inverse does. In general, any function that reverses the effect of f in this way is expressed by the inverse of f. All right, these observations are expressed precisely the following way. If you ever want to check to make sure you have the inverse right, if you take f inverse of the original function, f of x, you should get x, okay? They should undo each other and you should just get x. Similarly, if you take f and you plug in the inverse function, it should just give you x every time, okay? That's one incredibly important inverse function property that we have here. All right, let's talk about now how you find inverse functions, okay? There's a procedure for doing this. All right, so let's examine how we compute inverse functions. All right, we first observe that by the definition f inverse that y is equal to f of x. So then by extension, f inverse of y is equal to x. All right, so if y is equal to f of x, and if we are able to solve this equation for x in terms of y, then we must have x is equal to f inverse of y. If we then interchange x and y, we have the inverse function, which is our desired equation. Okay, so here's how you're going to find the inverse function. All right. First step, you're going to write y is equal to f of x. Then you're going to solve this equation for x in terms of y, if possible. All you're going to do then at that point is interchange x and y, and then resulting equation y is equal to f inverse of x is your answer. All right, so note that step 2 and 3 can be reversed if you want. So you can interchange y and x and then just solve it. It doesn't matter which way you do it, okay? The steps 2 and 3. All right, so let's find this inverse function here. Okay, so let's find the inverse of f of x is equal to 3x minus 2. All right, so first you're going to write it as y is equal to 3x minus 2. Next, what you're going to do is you're going to solve this equation for x. You want to get x by itself. So you're going to take this negative 2 and add it over. And then all you're going to do is divide by 3. So you're going to have x is equal to y plus 2 divided by 3. Finally, all you're going to do is just, you're going to flip the variables. Okay, so notice it was x is equal to y plus 2 over 3. You're just going to interchange the x and y, and you have y is equal to x plus 2 over 3. So therefore, this inverse function, all right, f inverse of x is equal to that x plus 2 divided by 3. And that makes sense, right? You're subtracting, now we're adding. You're multiplying, now we're dividing. It's the inverse, it undoes it. All right, so we got this inverse function. And now let's talk about finally how you graph these inverse functions once you have them. All right, the principles for interchanging x and y to find the inverse function also give us a method for obtaining the graph of f inverse of x from f. So if f of a is equal to b, then f inverse of b is equal to a. So thus the point AB is on the graph of f if and only if the flip BA is on the graph of f inverse. Okay, so if you want to graph, if you have the original function, if you want to graph its inverse, you literally just flip the ordered pairs. Okay. All right, so but we get the point BA from the point AB by reflecting in the line y is equal to x. Okay, so therefore, as figure 10 illustrates, the following is true. The graph of f inverse of f is obtained, is obtained by reflecting the graph of f along the line y is equal to x. So if in blue here, this is my original graph, here's the line y is equal to x, the inverse function is just the flip of it right here. All right, the reflection along this line. All right, let's do an example. All right, let's sketch the graph of f of x is equal to the square root of x minus 2. Let's use the graph of f to sketch the graph of inverse, f inverse, okay? And then finally, let's find the equation for the inverse. All right, so to sketch the graph of y is equal to the square root of x minus 2 by plotting the function of y is equal to the square root of x and then shifting it to the right 2 units. We learned how transformation in the previous section. All right, so here, this right here in blue, this is the graph of y is equal to the square root of x minus 2. All right, all you're going to do is you're going to find the graph of the inverse is obtained from the graph of f in part A by reflecting it along the line shown here. Another way to do this, like take this point here. This is the point 2, 0. Well, remember, 2, 0 becomes 0, 2 over here, and so on, and so on, and so on. Like the point 6, 2 would be the point 2, 6 over here, and so on, and so on. All right, finding the inverse equation here. All right, you're going to solve y is equal to the square root of x minus 2 for x. You have to note here that y is always going to be strictly greater than or equal to 0. So to solve here, what you're going to do to get rid of the square, you square root, you square both sides. Then what you're going to do is you're going to add the 2 over. All right. And then finally, the last thing you're going to do is you're going to interchange x and y, and you have to maintain that x has to be greater than or equal to 0 here, okay, because that's what y was. So this right here is our inverse function. All right, so thus the f inverse here is x squared plus 2 as long as x is greater than or equal to 0. And you see that x has to be greater than or equal to 0 in this graph here, right? Like the red graph, the inverse graph has nothing for the negative x values. All right, I hope that helped as a quick introduction to inverse functions.